Okay, let me just get back to one point this morning, because there was some discussion at lunch and I think maybe I got misunderstood. When we I said that the anomaly can be relevant or irrelevant. It's irrelevant if we can add a local counterterm to the action such that the variation of this counterterm cancels the anomaly. What I meant by a counterterm is some local term, some action S, which is something, of course, has to be some integral of some delta L, which is polynomial in the fields and in the momenta. That's what we mean by a local term. I called it a counterterm because in order to cancel the anomaly, this has to be some order G cubed term, right? So what I mean by a counterterm is something which is higher order than the original tree-level term. While I think you had in mind that the counterterm was something that is diverging and which cancels some diverging piece, okay? So of course there are the counterterms we add in renormalizing the theory, which have cutoff dependent coefficients, and then there's this other sort of counterterms that are also higher order than the coupling constant, and which are not diverging because our anomaly is finite, but which would have to be non-gauge invariant so that its gauge variation would cancel the anomaly. Okay, so just wanted to mention this point that the word counterterm is used quite generally. It doesn't have to mean diverging terms. Okay, so we have done this very detailed one-loop computation. I wanted to take some time and really show you that you can do the computation from A to Z and find and compute this triangle anomaly, and it's not that complicated. So, and we have found a rather generic form of the anomaly. I did it for a left-handed, by which I mean positive chirality fermion. So this was my psi L, and we found a contribution to the anomaly is -1/24 pi square epsilon nu rho sigma d mu a nu a nu beta d rho a sigma gamma, and then we had this d symbol dr alpha beta gamma, which was this trace of t alpha, t beta, t gamma symmetrized in the indices. Okay. Now we had determined this piece quadratic in the A's, and then there is some order a cube piece, okay, which I didn't compute. We would have to do a box diagram computation to determine this piece, and I didn't because we will later on show that there's a certain consistency condition on this anomaly has to satisfy, which is some sort of differential operator acting on the anomaly, which has to vanish. So that will give us some relation between these terms quadratic in A and cubic in A, and which will actually fix these terms in terms of these quadratic terms. Okay, so because they will be fixed, let me already write what is the result, although we don't know it yet. Okay, so first of all, this d mu here, I may write it like this, because, well, if it acts on A nu, it gave the term we had, and if it acts here, we get d mu d rho, which is symmetric in mu and rho, and this is killed by the epsilon, which is antisymmetric. Okay, so the additional term, I just increase the size of my bracket, and I'm gonna add the term which is cubic in the A's. So, well, 3 A's, we need nu rho sigma, so we're gonna have A nu, A rho, A sigma, but we only have 2 indices beta gamma, so I put a beta here, and here I take the commutator component gamma, and there's a minus I over 4. Okay, so that's what we're going to find. And there's no term with 4 A's, no term quartic in the A's, okay? And in particular, this is not F mu nu F rho sigma, okay? So this is what we're going to find. And I put an L here to remind you that this was for a left-handed fermion, okay? So this is a rather generic expression. The only thing we have to know is in which representation of the gauge group my fermion is in, compute the corresponding D symbol, and otherwise we always have exactly the same expression with the same minus 1 over 24 pi square and so on. You may wonder why a left-handed particle 1 and a left-handed particle 2 should have the same form of the anomaly. Well, if you think a little bit about it, they had to be massless. So there's no mass that can make a difference between different particles. And once you take away the mass, the only way two fermions can be distinguished is that they carry different representations of the gauge group or of any other flavor group or so on. So all this goes into this group theoretic factor to this D symbol. The rest is universal, okay? So we always find the same thing. Okay. One other comment, we got this from this one loop computation, and you may ask yourself, okay, this is one loop, why not look at 2 loops, 3 loops, any higher loops? Well, first of all, of course, we only did this, we only integrated out the meta fields, okay? So this is psi bar in A, and this thing, of course, is some psi bar L d slash psi L. It's quadratic in the meta fields, so the only thing this can give is a one loop term, okay? So I argued it's sort of the determinant of this d slash. Well, it's d slash PL, which doesn't really exist, but a determinant, once you write it as e to the trace log, because it's a question that you could rescale your action with a loop counting parameter, there's no lambda here, this always corresponds to a one loop term. And of course the way you compute such a functional integral quadratic always gives you a one loop thing, okay? If you expand this determinant and the trace, you generate all sorts of one loop terms. There's no two loop. But of course, after having done this, so this is my e to the I w tilde of A. This goes into my full action, because at the next step, I want to integrate over my gauge fields. Okay, so then I will have to deal with all the stuff of the A's and the ghosts and the anti-ghosts. E to the I, here I get a minus a quarter trace F mu nu, and the gauge fixing, the ghosts, and here I have my W tilde of A. Okay, so, and then of course, depending what you do, you insert here whatever A to compute endpoint functions of the gauge fields. So at this point, for example, my W tilde will give me a, among others of course, a 5-point function, and then I may well put an internal gauge propagator between these two vertices, and this will also contribute to the 3-point function. So you may wonder, okay, why do we only look at this one loop 3-point function and not at some 2 loop 3-point function? Can this also be anomalous? Can this give me some other contribution which I should add to this anomaly? Well, the answer is no. The anomaly only occurs at one loop, because here we had a problem in regulating this. We did Pauli-Villars, but this was problematic with only the left-handed fermions, so we had to add in the right-handed ones. But this one here, which has an internal bosonic propagator, gauge propagator, we may actually do Pauli-Villars on this line by adding a massive gauge Pauli-Villars field. Now you may think that adding a mass to a gauge field of course destroys the gauge invariance, but it doesn't destroy any of the important properties of this 3-point function. So we may just regulate this by Pauli Villars, and it will preserve the gauge invariance of this 3-point function. So any higher loop functions necessarily contain internal gauge boson lines, and they can always be regulated in a gauge invariant way. So the anomaly is always only one loop. This, and so on. Okay? So the anomaly is one loop. Now, in a given theory with a certain meta content, we may just then look what are the chiral fermions and what do they contribute to the anomaly. Now, as I said in the very beginning, if we have some global symmetry and it's anomalous, okay, it just means that this is not a symmetry, and then certain processes that are otherwise forbidden can occur, and there's nothing bad about it. Now, in the gauge theory, if my W tilde of A, which I should add to the -1/4 trace f mu nu, as I wrote and I just erased, if this is not gauge invariant, then the effective action for the gauge fields to be used is not gauge invariant, and all the usual rewritings and so on you do don't work, and you will at some point find that either your theory is not Lorentz invariant or it's not unitary, you get negative norm states, any of the bad things you don't want. So that's certainly a disaster, and if you try to build a model of particle physics and you have computed your W tilde of A and you find there's an anomaly, well, then the only possible option is you take your theory, you go to the garbage bin, and you start over again. Okay? So what we need is that either there are no chiral fermions. Well, if you look in nature, there are many chiral fermions, so that's not what's happening. Or actually, somehow these anomalies have to cancel. Okay? Now, if you have many chiral fields, your e to the I W tilde of A is, of course, there's some chiral field psi1, and then you have some other field psi left 2, and maybe you have some right-handed fields 3 psi r3 bar e to the I L meta, which contains all those fields. Okay, so you look at the measure for these guys, and they may have some anomalous contribution, some anomaly for particle type 1, and they may have some anomaly for particle type 2. Because they all come as the exponential of something, they will obviously then combine into e to the I the sum over the different particle types I, and the anomalies add up. Okay? So what we need is to compute the total anomaly of all the chiral particles. And if we are lucky, this total sum will be 0, and we say the anomalies have cancelled. So this was the expression for a left-handed anomaly, and it's important that it's relatively universal, because the only thing we need to add then are these d symbols. Okay? That is for left-handed. If I had done the computation for a right-handed, so then my PL would have been changed into a PR, and the 1 plus gamma 5 over 2 into a 1 minus gamma 5 over 2. So the anomaly, the epsilon, came from the plus gamma 5, which then gets replaced by a minus gamma 5. Okay? Otherwise, the computation is the same. So then the anomaly for a right-handed particle just gets an extra minus sign. Okay? So A alpha for a right-handed chiral fermion is just minus the anomaly of a left-handed fermion, which otherwise comes in the same representation of the gauge group. Okay. So then, if we ask the question of whether the total anomaly cancels, but some trivial cancellation, of course. If I have a left-handed fermion in some representation R, and a right-handed fermion in just the same representation R. Obviously they will cancel, but that's just like taking a non-chiral fermion, having split them into left-handed and right-handed, and treat them separately. Okay, so I can always take a non-chiral Dirac fermion, split it into left and right, and I know the anomaly cancels. So what I really need to look at the total sum of all the particle types and sum up all the, so I need to look at the sort of in the left-handed set. So I have my anomalies left-handed for type I, okay, and then minus all the contributions of all the right-handed ones. Well, I should add the right-handed ones plus the right-handed J, but I know the right-handed are just the opposite of the left-handed ones, okay? Okay, now, so what really comes are these D symbols. Okay, so here I get the sum of all the D symbols for the left-handed in representation Ri, alpha, beta, gamma, all the left-handed in these. Let me write this RL for the left-handed representations, and the right-handed one, though they contribute to the minus sign, and I get a sum of all the J's right-handed of the right-handed representations alpha, beta, gamma. Okay? Okay. Now, if you have some fermions transforming in some reducible representation, okay, then the trace in, so if R is a sum of Rj's, then this trace, of course, is just the sum over J of these traces in Rj of T alpha, T beta, T gamma. So it's some big representation matrix, which is block diagonal. The trace just splits into traces over the individual blocks. That's just this statement here. Okay, so at some point, the question of whether the anomalies cancel boils down to knowing what are all the representations of your left-handed particles and what are all the representations of your right-handed particles. Okay, now comes a little subtlety. If your particle, so for example, the neutrino, you know the neutrino is left-handed, okay? The neutrino is left-handed, and in the standard model it comes in some non-trivial representation. It's part of a non-trivial representation of SU2. But you also know that the antineutrino is right-handed. So then, what is the contribution of the neutrino to the anomaly? Shall I look at the left-handed neutrino? Or maybe should I think, because we arbitrarily decided that one particle type we call the particle and the other we call the antiparticle. We could well have thought of the antineutrino to be the particle, and then we would start out with a right-handed one, okay? So, because left-handed and right-handed contribute with opposite sign to the anomaly, it looks like we don't really know. And of course, we should not include both. It's not that you add the anomaly of the left-handed neutrino plus the anomaly of the right-handed neutrino. Because when we do a Feynman diagram computation, our propagator, the propagator, of course, is the propagator for the field, and the field contains at the same time the propagation of the particle and of the antiparticle. Right? If you compute a one loop for electrons, we never add a loop for electrons plus the loop for positrons. So we should treat them together. And it looks like we are stuck. We don't know whether it's left-handed or right-handed. But of course, there's a simple solution. If we decide to treat the neutrino as the particle and it's left-handed, then that's described by some left-handed chiral spin-up psi L, which transforms in some representation R, L, I put L to remind you that was my left-handed particle, of the gauge group, okay? Now, if I want, instead of treating the neutrino as a particle, I would like to work with the antineutrino, I should use the charge conjugate spinner, okay? I should use the charge conjugate spinner of the neutrino, because that describes that sort of describes the antineutrino as the basic object. Now, how do we get the charge conjugate spinner? Well, you know, the charge conjugate spinner is I gamma 0. There's a charge conjugation matrix, and we take psi complex conjugate. That's how we make a, well, in general, let's not put the L yet. For any Dirac spinner, the charge conjugate spinner is this one, okay? So let's just check that this thing has opposite chirality from this one, okay? Now my charge conjugation matrix satisfies gamma mu transpose equals minus gamma mu. Okay, that's how I define my charge conjugation matrix. That it relates gamma mu and the transpose with a minus sign. And because gamma 5 is a product of all the gamma matrices, of the 4 different gamma matrices, you find that C with gamma 5 transposed is plus gamma 5 C. Okay? This also involves, when you transpose, you get the 4 matrices in a different order. You have to reorder them, and you get an even number of minus signs. So that's why you end up in the end with a plus here. Okay. Now, if this is left-handed, okay, which way I do it? Okay, so let's see what is gamma 5 acting on my charge conjugate spinner. So it's gamma 5, I, gamma 0, C, psi star. The gamma 5 goes through the gamma 0, gives me a minus sign. So this is minus I, gamma 0, gamma 5, C, psi star. And then gamma 5C is gamma 5 transpose, so I can flip them. So that's minus I, gamma 0, C, gamma 5 transposed psi star. But gamma 5 was Hermitian, so transpose is the same as complex conjugate. So I put a complex conjugate. Okay. So gamma 5 complex conjugate psi complex conjugate is just gamma 5 psi complex conjugate. Okay. Let's continue here. Now, if gamma 5 psi is plus minus psi, which means it's right or left-handed, then what I get here is minus I gamma 0 C plus minus psi complex conjugate. So with this is minus plus I gamma 0 C psi complex conjugate, but that was my charge conjugate spinner. So that's minus plus psi charge conjugate. Okay? So we find that gamma 5 on the charge conjugate spinner is minus plus. Okay? So this has the opposite chirality from the original spinner. And that's what I wanted to show. If the neutrino was left-handed, the antineutrino is right-handed. Okay. Okay. But what about the representation of the gauge group under which it transforms? Well, if my neutrino, my particle, transforms in some representation R, that means that psi under gauge transformation goes to e to the I theta alpha T alpha psi. Okay. So then what about the in some representation here? Okay. So what about the charge conjugate? The charge conjugate involves psi star. So psi star goes to the complex conjugate. So e to the minus I theta alpha T alpha R star on psi star. Okay. Now my generators were Hermitian. So star is the same as transposed. So this is e to the I theta alpha. I put the minus here, minus T alpha R transposed psi star. So we could say that the psi star transforms with generators that are minus T transposed. Okay? So we say these are the complex conjugate representation. So the T R star alphas are minus T R alpha transposed. Okay? But then, if I want to compute the anomaly in terms of the charge conjugate spinner, so I suppose I grew up on Mars, and on Mars we decided that the antineutrino was the particle. Okay, so I'm reasoning in terms of the charge conjugate spinner. It's a right-handed particle, negative chirality, transforming in that representation. So for the anomaly, I have a minus because it's right-handed, it has opposite chirality, and then I need the D symbol for this complex conjugate representation. So I have the minus for the opposite chirality, then I get a trace of these T alpha R star, T beta R star, T gamma R star. But I get 3 minus signs and the transposed. So there's this minus sign, there are 3 minus signs for each of these generators, and then I get a trace of T alpha R transposed, T beta R transposed, T gamma R transposed. Well, symmetrized. They're all symmetrized in alpha, beta, gamma. So first of all, I have 4 minus signs, so that's a plus. And then that's the trace of, well, transpose, transpose. I can reverse the sign, so that's T gamma R, T beta R, T alpha R transposed. Okay, but because I symmetrize in all the indices, it doesn't matter in which order I write. And the trace of a transposed matrix is the same as the trace of a matrix, because the traces, you just sum the diagonal elements, and whether you transpose it or not, it doesn't change anything. So this is the same as the d alpha beta gamma for the original representation. Okay, so we see it doesn't matter. We can say we take the neutrino, which is left-handed, and compute the d symbol, or we can take the antineutrino, which is right-handed, so we get 1 minus sign, but the representation is different. It's the complex conjugate representation. We get 3 other minus signs, and in the end we get the same thing. So fortunately, it doesn't matter whether we take a left-handed particle or we use the right-handed antiparticle. It contributes the same thing to the anomaly. Okay. Okay, so then we have, well, these arguments, I did them in 4 dimensions, but we'll be interested more generally in anomalies in arbitrary dimensions. So let's see what happens. Well, first of all, what is okay in 4 dimensions? Well, anomalies are only in even dimensions. So we're interested in 2, 4, 6, 8, 10, and so on. Okay. So this relation about the gamma 5 and the charge conjugation, I said it involves reordering. When you take the transpose of gamma 0, gamma 1, gamma 2, gamma 3, you get the gamma 3, gamma 2, gamma 1, gamma 0. You have to reorder them. So you get 3 plus 2 plus 1 plus, so that's 6 permutation. You get 6 minus signs. If we were instead in 3 plus 2 plus 1, yes. If we were in 2 dimensions, for example, we would just have 2 matrices. So when reordering, then we get 1 minus sign. So you get an overall minus sign. In 6 dimensions, reordering gives you 5 plus 4 plus 3 plus 2 plus 1. So that's again an odd number, you get a minus sign. And in 8, you get a plus. So this sign here is plus in 4 mod 4 dimensions, and it's minus in 2 mod 4 Okay. So otherwise the charge conjugation is defined in the same way. So what you find is that in 4 mod 4 dimensions, psi and psi c, the charge conjugate, have opposite chirality. Okay. Well, in 2 mod 2 dimensions, in 2 mod 2 you get a minus sign here, and you got a minus sign from moving the gamma 5 to the gamma 0. So in 2 mod 2 dimensions, psi and psi c have the same chirality. Okay. Now, in 4 dimensions, we needed the D symbol with 3 indices. In general, if D is 2R, they are R plus 1 indices, because we looked at the R plus 1 point function. Okay. So if we are in 4 mod 4 dimensions, we'll have 3 or 5 or 7 indices. And when we go from a representation to the complex conjugate one, we get an odd number of minus signs from the D symbol, and we get a minus sign from the switch in chirality. So again, we get an even number of minus signs. Okay. So again, in any dimension which is 4 mod 4, it doesn't matter whether we take the left-handed particle or the right-handed antiparticle. Now if we are in 2 mod 4 dimensions, so 2, 6, 8, 2, 6, 10, sorry, 2, 6, 10, 14, the particle and the antiparticle have the same chirality. Psi and the charge conjugate spin have the same chirality. But the number of indices in this D symbol now is even. We have 2, 4, 6 indices. So they give me an even number of minus signs doing the same manipulation. And again, it doesn't matter whether I use the particle, which is left-handed, or the antiparticle, which is also left-handed. They have the same D symbol. Okay? So in any case, it doesn't matter. Now, yes. Just as a remark, we may define, well, sometimes we use Majorana spinners, which means essentially that we say psi equals psi c. Okay? But of course, in 4 mod 4 dimensions, we can't do this for a chiral spinner because psi and psi c have opposite chirality. But in 2 mod 4, because psi and psi c have the same chirality, it may happen that we can identify psi and psi c and not only have chiral spinners but also Majorana spinners. Well, it's a little bit more subtle. You can't do it in every 2 mod 4, but in 2 mod 8, you can have Majorana Weil spinners. Majorana means psi equals psi c, and Weil means of some of one or the other chirality. Okay. So if you have a Majorana Weil spinner, well, morally it's like 1/2 of a Weil spinner because you impose this additional condition. So in this case, the expression for the anomaly, you need to divide it by 1/2 because you have just half as many components in your spinner. But that's sort of a special case. Okay, so now you know essentially everything in any dimension. So we still need to ask for which representations and for which gauge groups. Well, it may happen that these D symbols just vanish, okay, in which case there's no anomaly. So we have to check, we have to take a book on group theory and the representations and find some table or some rules which tells us which representations have vanishing D symbols and which representations have non-vanishing D symbols. Well, actually, well, D symbols depends on D symbols with how many indices. So let's go back specifically to 4 dimensions. So now we need to look at the D symbols with 3 indices in representation R. And things are actually pretty simple. Well, one thing I just showed you is that the D symbol for the complex conjugate representation equals minus the d symbol for the corresponding representation. Okay. Now, a representation is called real or pseudo-real, real or pseudo-real. That's just some terminology. If there exists some fixed matrix S such that the T's of the complex conjugate representation are related to the T's of the representation R by some similarity transformation. Okay? But these guys, we've just shown that they are minus T alpha R transposed. Okay? So then obviously for such a real or pseudo-real representation, if I compute the D symbol, the D symbol for the R star representation, which by this thing is just minus the D symbol of R. But if my R star generators are related by similarity transformation to the T's, this is also plus D alpha beta gamma R. So D equals minus D. So for a real or pseudo-real representation, the D symbol with 3 indices vanishes. Okay? So then you go to a book about representation groups, and you find that certain groups only have real or pseudo-real representations, which means that all their D symbols vanish. Okay? For all representations. So that's easy enough. So now we can make a list. Well, in gauge theories, we are almost always interested in compact groups. Okay? So, and then the groups, our gauge group is always a product of some simple groups, GS, and certain number of U1 factors, N. Okay? So, the simple groups are, well, we have the SUN groups, we have the SO2N, we have the SO2N plus 1, we have the SP2N, and then we have these exceptional groups G2, F4, E6, E7, E8. Okay, and you go and look for the, so some of them only have real or pseudo-real representations. So let's see which ones. These ones have only real or pseudo-real representations. These have only real or pseudo-real representations. G2, E7, E8, F4. So they all have vanishing D symbols. So no anomaly. Okay. So we still have E6. Now among the SO2N, we actually have to distinguish between the SO. So 2N can be 4N, or it can be 4N plus 2. So if it's 4N again, only real or pseudo-real, so that's of no help. And then, so we're left with SUN, N larger equal 3, because SU2 is the same as SO3, so that's out. And then the SO4N plus 2 do have representations that are neither real or pseudo-real. Same for E6, but then again, for some other reason, the D symbol with 3 indices vanishes. So that's very simple. We are only left with SUN, N larger equal to 3, and U1. Okay? So for U1, U1 is particularly simple. For U1, well, the generators are just abelian, so there's just a single generator T, no alpha, and then trace, we have trace T, T, T. Well, the eigenvalue of T, usually we call it the charge. We write Q, okay? Now T, the irreducible representations for an abelian group, of course, are one-dimensional, but in general, this does not need to be a irreducible representation. We can have many representations, so this is just the sum over all the irreducible components of the T cube, which we usually call Qi cube. So for an abelian group, the D symbol is just the sum of the charges squared, electric charges or other, right? Whatever are the U1 charges. And then we have SUN, which has a non-vanishing D symbol. Okay. Now, our gauge group can be some product group of this, okay? The gauge group can be a product group of any of these groups, so it's a little bit more complicated. For example, if we have a product group, well, group number 1, group number 2, group number 3, okay? Suppose this is our gauge group, it's a product of 3 groups. Then we have gauge bosons for any of these groups, okay? And in particular, we can look at a triangle diagram where here we attach a gauge boson, say, of G1, here we attach a gauge boson of G2, and here we attach another gauge boson of G2, okay? So in this case, the corresponding D symbol is the trace over some big reducible representation, or whatever, I mean, of the product group. So here we have, so if this is alpha, this is beta, this is gamma, we have a generator T alpha of G1, and then we have generators T beta and T gamma of G2. Okay? So now these generators don't talk to each other, so the trace factorizes. Okay? That's a trace of T alpha, and then we get a trace of T beta, T gamma. So that's like a D symbol just with 2 indices, but the trace T beta, T gamma is non-vanishing for every group, because that's just delta beta gamma, okay? That's just delta beta gamma times the corresponding normalization in this representation. Now the trace of just a single generator for any simple group vanishes. It's only for U1 that this is non-vanishing, in which case we get the charge. Okay, so this must be U1. So although if we put the gauge bosons of the same group, it must be either all U1 or all SUN, but if we put one U1, we can have GG for any group. Okay. So, well, this discussion is of interest because if you think of the standard model of electroweak interactions, our gauge group is SU3 cross SU2 cross U1. Okay. So then we have many possibilities to check for anomalies and, well, to check actually for anomaly cancellation. So we have an anomaly where we put SU3, SU3, SU3 gauge bosons at all 3 vertices. That's okay because SU3, so then we have to look at the D symbol of the SU3 representation. Okay. Now, the other, we cannot put SU2, SU2, SU2 because SU2 is SO3, which had a vanishing D symbol. But we can have the case where we put a U1 gauge boson here, and then SU2 here, and then SU2 gauge boson there. Okay. So this will give us, well, I, that's U1 charges, and then we get the trace of the SU2 generators, which gives me a delta beta gamma, the corresponding C in corresponding representation I. So I break my representation to irreducible components I. I have the same thing, of course, for U1, SU3, and SU3. Okay, so this was for SU2. Same thing for SU3. We have to check for U1, U1, and U1. And there's a fifth one, which I forgot. U1, U1, GG. No. No, that's it. That's it, okay? So in the standard model, we have to check for all these anomalies. All these diagrams can potentially give rise to anomalies. So then it's a rather simple exercise to make a list of your particle content in the standard model and check that all the contributions to the anomaly cancel. Okay, so let me make the list. Well, you know that in the standard model, the particles come in generations. There's a first generation with the electron neutrino, the up quark, and the down quark. And then you have a second generation and a third generation, and things repeat. Okay, so well, the quarks transform under SU3, the color symmetry of QCD. The electron and the neutrino transform under the SU2. They go into doublets, or some particles are singlets. And then there's this hypercharge U1. Okay, so let me make a list table. So here's my SU3 representation. Here is the corresponding SU2 representation. And here comes the U1 representation, or the U1 charge, which is the hypercharge. Okay. So then we have the left-handed neutrino together with the left-handed electron. Well, they form an SU2 doublet. So here we put a 2. Well, they don't have strong interactions, so they are singlets under the SU3, and the hypercharge is 1/2. Well, then we have the right-handed, there's no right-handed neutrino, but there's a right-handed electron. Okay. Now the right-handed electron, we may either describe it as a right-handed electron, or we may look at the charge conjugate, which is a positron, and which now is left-handed. Okay, the representation. So this is a singlet. It's a singlet, and the hypercharge. Well, the positron would have a positive electric charge. Well, that's not electric. That's the hypercharge. But because I take the antiparticle at the opposite, and you will find that the hypercharge is -1. Okay. So then for the quarks, they're up and down, left-handed. They make an SU2 doublet. And of course, it's a color triplet. Okay, and the hypercharge is -6. And then we have the right-handed, and again, the right-handed U quark. I describe it by the charge conjugate antiparticle. So instead of being in the 3 representation, because it's the antiparticle now, I get the 3 bar, the complex conjugate. Okay. It's an SU2 singlet, and the hypercharge is 2/3. And lastly, well, if you can read, there's the D right-handed, which I again describe by the charge conjugate. So it's also in a 3 bar. It's a singlet of SU2, and I get a -1/3 here. Okay. Okay. So you may check for any of these anomalies. Okay. So for the SU3 anomaly, well, those that do not transform under SU3, of course, do not contribute. If they are singlets, it means that the corresponding generator is 0, so no D symbol. So you only need to look at the quarks that transform non-trivially, okay? So you have this SU2 doublet, which means that with respect to SU3, you just have twice the 3 representation, and these guys have twice the 3 bar representation. So the quarks will give me 3 + 3 + 3 bar + 3 bar, which is again a real representation because it's 3 plus the complex conjugate, and we know that if we sum the d symbols we get 0. Okay. So this gives us 0. And the others contribute. So for example, for the U1, SU2, SU2, okay, so we need to go through the list. We multiply the U1 charges times the, then we look at the only the SU2 doublets contribute. So let's see, we have this one and we have this one. So we get a half times the C coefficient for the 2 representation. And here we get a -6, but they are SU3 triplets. So we get again 3 times this one. And because plus a half and minus a 6 times 3 cancel, this anomaly also cancels. And you can look for the other ones, in particular the U1 cube. You have to take the cubes of all the U1 charges times all the multiplicity, and you find again that they all cancel. Okay? So all the possible anomalies of all the possible chiral particles in the standard model just cancel. Now, just historically, of course, when people discover the particles of the second generation, there was the strange quark, but they haven't seen the charm quark, so one quark was missing. So then it's like, say you didn't have the D quark here. So then, of course, you didn't think that this was in an SU2 doublet. It looked like this was an SU2 singlet. And then if you do the same thing, well, the SU3 anomalies are okay, but the U1 SU2 SU2 anomaly would not appear to vanish. So this was this famous charm problem that was solved by discovering the charm, and then the total anomaly again cancelled. Okay, let's make the break now, because I start a new chapter afterwards. Okay. Yes, okay. So, second part of the lectures. So the next part of the, you may think that so far not everything has been very explicit, but it was still relatively explicit. And now I want to go to more formal aspects of anomalies, which will allow us at some point to discuss anomalies in arbitrary dimensions, and also more or less discuss gravitational anomalies. And we will also, one of the things we need to do is fix the cubic term in the anomaly by some consistency condition, which will be this Wessomino consistency condition. We want to reformulate things a little bit, so there are various things we want to formalize now. So the first thing is that you may have noticed that my anomaly, my gauge anomaly, which was minus the divergence of the covariant divergence of my expectation value of my current. So this was minus 1 over 24 pi squared, epsilon mu rho sigma, the trace in my representation of T alpha d mu a nu d rho a sigma plus this order a cube terms. Okay. Now, this epsilon mu nu rho sigma d mu a nu d rho a sigma, at least for if this were an abelian theory, you would think that, well, that looks like something f tilde or f wedge f in terms of differential forms, okay? So the first thing is we want to introduce the language of differential forms, and to rewrite the anomaly as some differential form that will be very convenient. And there will be a couple of formal developments related to forms. Let me spend some time, maybe it's useless because you all are familiar with differential forms, but let me spend some moments introducing differential forms, okay? So I have some d-dimensional space-time, and I have some symbols I call dx mu, and they are such that there is some wedge product which is antisymmetric. So whenever I exchange two of these symbols, I get a minus sign, okay? And you have more of them, you can have 3 dx mu, which dx rho, and so on, an arbitrary number. Now we define a p form to be the following thing, psi p. We take an antisymmetric tensor with p indices and we multiply it with this dx mu1 wedge dx mu p, and that's completely antisymmetric. There's some sort of overcounting, and we divide by the number of permutation, which is p factorial, okay? Okay, we can define the product of some p form with some q form just by multiplying things together. So this is a 1 over p factorial, 1 over q factorial. I get the psi mu1 up to mu p. I get the zeta nu1 up to nu q. And then I just get the product of all my dx mu1, dx mu p, dx nu1, dx nu q. Now, because that's antisymmetric, in d space-time dimensions, I can have at most d of these symbols. So the maximum degree of such a form is, of course, d, okay? So if p plus q is more than d, this thing necessarily vanishes, okay? Because that's completely antisymmetric, it will automatically completely antisymmetrize all the indices here, okay? Now, an important thing is how these objects transform under coordinate transformations. If I change my coordinates, well, under coordinate transformations, the different fields can transform as scalars, vector fields, tensors, and so on. Now, this transforms as an antisymmetric tensor, but under a change of coordinates, if I go to some x prime, well then, this is dx by dx prime, so they also transform now as an antisymmetric tensor, this as a contravariant, this is a covariant tensor, and because I'm summing over the indices, this actually constructs a scalar, okay? So a p form is a scalar. Is a scalar under coordinate changes, okay? Now, in general, we will not just be interested in flat d-dimensional Minkowski spacetime, but on some arbitrary curved manifold spacetime. And on an arbitrary curved manifold, we usually need to introduce several coordinate patches. So some coordinate patch u1 or ui, some coordinate patch uj, and we have to ask what happens in the overlap. We have to know how the p form written, so here I have coordinates x, here I have coordinates prime, so here I write my psi in terms of the x's, here I write my p form in terms of the x prime, and in the overlap I have to relate them. Because they are scalars, the relation is very simple, okay? For a scalar, there's nothing to be done. The psi in terms of the x coordinates just equals the psi in terms of the x prime coordinates, okay? So that's the why p forms are interesting, because they transform very simply just as scalars. Okay, now, well, very often we need to take a derivative of something, and on forms what acts naturally is the exterior derivative, which is dx mu d by dx mu, dx mu d mu. Okay. So if we act on some p form, because there's one more dx here, we get a p plus 1 form. So d on psi p, 1 over p factorial, d mu psi mu 1 mu p, and then we get dx mu 1 dx mu p, and because that's antisymmetric, we have to antisymmetrize the indices. Okay. Now because of this, if I take one more derivative, dd of psi p, I will get something here which is d mu d nu psi antisymmetrized, but d mu and d nu commute, so this is 0. Okay. So quite generally, this d, which is called the exterior derivative, it squares to 0. Now, so here comes an interesting question then. If I have a p form such that d of it is 0, we say it's a closed, the form is closed. Okay? We say that psi is closed. Now, on the other hand, if psi is d of some p minus 1 form, we say that psi is exact. Now obviously if psi is exact, then d of psi p automatically is 0, because this is d of zeta p minus 1, and d square is 0. So any exact form necessarily is closed. Okay? So the interesting question then is, if I have a closed form, if d psi is 0, well, maybe it's 0 because psi is d of something, it's exact, or maybe not. So the interesting question is whether any closed form necessarily is exact or not. Well, that depends. And so we define the space of, so this brings us to the notion of cohomology, or the Ram cohomology, which is, we say that we are looking at closed form. So we're looking at closed forms, and we say that psi p, there's an equivalence class up to adding exact forms. Okay, so the equivalence classes of closed forms, modulo exact forms, is called the pth Durham cohomology group. Okay, well, that's a vector space, and there's a certain dimension of such closed forms up to equivalence class by exact forms, and the dimension of this pth cohomology class is called BP. It's called the Bth Betti number. And well, how many such closed modulo exact forms exist is actually a question of the topology of your space. Okay, so these BPs, which are called the Betti numbers, are called also the Betti numbers of the manifold. So let me give you some examples. Okay, let me give you some examples. Well, actually these exterior derivatives you're sort of familiar with from ordinary vector calculus, which you learned in first year mathematics, because this exterior derivative is a little bit like taking the rotational or the curl. Okay, so if you have a zero form, if f is a zero form, then df is just d mu f dx mu. So this is like the gradient. Okay, the components here are like the gradient of f. Okay, and then if you have a one form, psi 1, and you take the exterior derivative of this, so this is d mu psi nu minus d nu psi mu dx mu dx nu. So that's like taking the curl of a vector field. Okay, Okay. Now you know from classical calculus that the curl of a gradient is 0. That's just the statement that d of df is 0. Okay. The curl of the gradient of f is 0. That's the statement d square equals 0 on 0 forms. But d square equals 0 is valid on any degree of form. Okay. Now, you also learned in first year calculus that if you have a vector field and its rotational is 0, then this field is the gradient of something, right? You learned in electrostatics that the gradient of E is 0 in statics. And you concluded that E was minus the gradient of phi. So that's the statement, but that's true in statics. That means you are in R3. Your manifold is R3. So the statement is that on R3, a closed one form is exact. So we would say that that B1 of R3 is 0. Any closed one form is exact. But, well, that's not always true. It depends on the topology of your manifold. Okay? Okay, let me give you some other examples. Let's see what's that example here. Yeah, another example from classical electrodynamics. Okay, so let A be a one form. So A mu dx mu. Okay, so that's some abelian gauge theory like electrodynamics. Then dA, well, that's 1/2 d mu a nu minus d nu a mu dx mu wedge dx nu, which is, this is just f mu nu, so that's 1/2 f mu nu dx mu dx nu. Okay? And in particular, if A is d phi, that's just a statement that A is the gradient of something. So we say A is pure gauge, right? This is pure gauge. Well, then F, which is dA, which is d square phi, is 0. And we know that because A was pure gauge, the corresponding field strength must vanish. Okay? Okay. So what's my next example here? Here it goes. Yeah, okay. So now let's see what happens with the converse. Suppose F is 0. Okay. So F is defined as dA. That's the definition. So if F is 0, that means that dA is 0. So A is closed. The question then is, if A is closed, is A necessarily exact? So is A pure gauge? Okay. So let me show an example where that's not true. A very familiar example from classical electrodynamics. So here we go. We take a solenoid, infinitely long. You have a current going through this wire. So you know with an infinitely long solenoid, you have a magnetic field which is confined inside the solenoid. Okay? There's no magnetic field outside because that's infinitely long. So now I take as my space-time or space, because we're in a static situation, we forget time. So M is R3 without the cylinder, without the solenoid. Okay? So my manifold is all the space outside the solenoid. Okay. Now, because there's no magnetic field outside, I know that on M, well, on M, of course, I'm only looking what's happening on my manifold M. So on M, F is 0. So dA is 0. So A is closed. A is closed. Well, that's just written there. Question, does it mean that A is exact? If A is exact, it means A is pure gauge. Okay? Well, we know what A is for the situation because my vector potential circles around the magnetic field, and clearly it's non-zero and it's not pure gauge. Okay? Suppose A were pure gauge. Well, if A were pure gauge, then I could compute the circulation of A I could compute the circulation of A around this circle. Okay. And if A was d of something, well, then this is A of dA, and then by Stokes' theorem, this would be the integral of A over the boundary of the circle, but there's no boundary, so this would be 0. Okay. On the other hand, we know that the circulation of A must equal the flux through this, the inside of the circle, and this is non-zero. So A cannot be pure gauge. Well, actually, you know what's happening here. You know if the magnetic field here is B, okay, if the magnetic field, the modulus is B, then A is something like B divided by 2 pi times d phi, where phi is the angular coordinate here. Okay. And then if I integrate A around the circle from 0 to 2 pi, I'd get just the flux of B. Okay, B is the flux, the total flux of a magnetic field. So it looks like A is d of something. It looks like this is d of B over 2 pi times phi, but phi is not something which is well defined. Okay, phi is an angular coordinate. It's not a function that is well defined on M, because you start sort of at 0, and once you've gone around your 2 pi, it's not something which is single valued. So when I say that a form is exact, it means it's d of something, and the something has to be well defined. Okay, so that's a standard example where my manifold has non-trivial topology. It's not simply connected. I mean, there are closed loops which I cannot shrink to a point, because I have to go outside of my manifold. And in these cases, non-trivial topology, not every closed form will be exact. So there's a, in this case, we have this B1 is 1. Okay? Okay. There's another standard example of closed forms that are not exact. If you have a compact manifold, M, there's always a form of maximal degree, which is the volume form. So for example, if M is a two-sphere, a standard two-sphere, okay, the surface of the Earth, you introduce phi and theta, standard spherical coordinates. So there's a two-form, which is sine theta d theta d phi, which is just the volume form. Okay, that's a 2 form. Obviously, d of omega would be a 3 form. There are no 3 forms on a 2-dimensional manifold, so that's 0. So the volume form is closed. But we know that the, well, I have to tell you in a second how we integrate forms, but the integral of the volume form is 4 pi. And if omega would be d of something, we would get 0. Okay, so the volume form never can be exact. Okay, well, how do we see that this is not an exact form? Again, you cannot write that this is d of sine theta d theta times phi, because phi is not well defined. Phi jumps by 2 pi, so that's not good. Okay, but you might think that this is d of cosine theta d phi minus, because if you take d of minus cosine theta, you get the derivative of minus cosine, which is sine theta times d theta. So it looks like this volume form is d of this thing. But again, this thing is a one form which is not well defined. Because d phi is like a little arrow like this. But at the north pole, we don't know which way d phi should point. Okay? So the one form d phi is not well defined on the north pole, and it's not well defined on the south pole. Now, in the volume form here, sine theta vanishes at the north pole. So the point where d theta is ill-defined, this thing actually vanishes. So this whole thing is well-defined. But cosine theta does not vanish at the north or the south pole. So you're not allowed to have a d phi there. Okay? Okay. Yep. Well, I already started to integrate these forms, so I should tell you how we integrate differential forms. Now okay, so we are on some d-dimensional manifold. Okay. Let's look at dx mu 1 up to dx mu d. Okay. This thing is completely antisymmetric in all the indices. So as such, it must be proportional to whenever I exchange two of the indices, I get a plus or minus 1. So that's I call this the pseudo-tensor epsilon hat mu 1 mu d, which is plus or minus 1, times dx0 wedge dx1 in the standard 0 to d minus 1. Okay? But that's just the volume of the infinitesimal volume element. Okay, so this thing I can integrate over my manifold. Now I can rewrite this in terms of the true epsilon tensor. Right? Remember that the true epsilon tensor mu 1 mu d is related by the square root of the determinant of the metric to this plus minus epsilon tensor. So I can rewrite this eps, and if I put the indices up, mu 1 mu d, I get a minus epsilon hat mu 1 mu d. So you can rewrite this epsilon hat in terms of the true tensor as, so this is epsilon mu 1 to mu d square root minus g, and this thing is just d dx. Okay, if you wish. Okay, so this thing is ready to be integrated over a d-dimensional manifold. So if I have my psi d, a d form, which is 1 over d factorial, psi mu 1 to mu d, epsilon mu 1 to mu d, square root minus g d dx. So this is a scalar. That's the invariant volume element. So that thing is ready to be integrated over my d-dimensional manifold. Similarly, if I have a p form, I can naturally integrate a p form over any p-dimensional submanifold. Okay? Okay. Now let me remark that originally my any p form does not involve the metric. To write it, it does not involve the metric. But this rewriting in terms of the epsilon tensor and the square root of the determinant, it introduces the metric, although originally there was no metric. So you can always integrate d forms over the manifold without ever having to talk about a metric. Okay, so Then we have simple things like Stokes' theorem. So Stokes' theorem tells us that the integral over some p-dimensional submanifold of D of some p minus 1 form, so that's a p form, which I can integrate over some p-dimensional manifold. Stokes' theorem tells me that this is the integral over of the p minus 1 form zeta over the boundary of this p-dimensional submanifold, okay? So that when I talked about the integral of the volume form, which was a 2 form, for example, over my 2-dimensional manifold, which was the sphere, well, when I said if omega had been exact, then this would be the integral of S2 of D of something, and then by Stokes' theorem, that would have been the integral over the boundary of the sphere of omega. There's no such boundary. You would have found 0, in contradiction with the 4 pi, which tells you that the volume form cannot be exact. Okay. Okay. So, using this language of differential forms, we can, for example, write f wedge f. Okay? So f is 1/2 f mu nu dx mu dx nu. Then wedge, we do not always write the wedge product. Okay? So we get another half f rho sigma dx rho dx sigma. So this is then a quarter f mu nu f rho sigma. And then I get dx mu dx nu dx rho dx sigma, which from the above identity is epsilon mu nu rho sigma square root minus g d4x. Okay? Okay. So we get exactly this type of combination we have seen for the anomaly. For example, for the abelian anomaly, we got epsilon mu nu rho sigma, f mu nu f rho sigma. And this was integrated with the d4x. Now we have a square root of g, because now we generalize to a curved spacetime. But on a flat Minkowski spacetime, of course, we don't have the square root of g, and we have this. And in particular, our anomaly the expression for the anomaly we had so if I just take dA, okay, so this is d mu a nu dx mu dx nu d rho a sigma dx rho dx sigma. So this then is again, it's a this gives me the epsilon, so it's epsilon mu nu rho sigma d mu a nu d rho a sigma square root of g d4x. Okay, so if I multiply then with a T alpha, which I can always do, T alpha, and I take the trace, so get the trace here, and that's a 4 form which I integrate over my manifold. I should put the epsilon here, so the epsilon alpha, that's exactly my anomaly, okay, up to the minus 1/24 pi square. So the anomaly will be very naturally, or the quadratic part in the gauge fields will be very naturally expressed in terms of this dA 4 form. Okay. Now, well, this is non-abelian, so let me say a couple of words about non-abelian gauge fields written as forms. Okay, so we introduced the gauge field 1 form A as A mu dx mu. But in the non-abelian gauge theory, these are matrices, okay? These are really A mu alpha T alpha dx mu. So this is a 1 form, but it's a matrix valued 1 form, okay? Now for ordinary 1 forms, because dx mu commute, if you had a psi 1 and a zeta 1, you could exchange the orders, because forms of odd degree anti-commute. But now, of course, because these are matrices, you have to be careful. Okay? You may still anti-commute the A mu dx mu with something else, but you have to keep track of the matrices. Okay. Now, A square, which is just meant to be A wedge A. Okay, so that's A mu alpha T alpha dx mu, A nu beta T beta dx nu. So this is antisymmetric in mu and nu. So I may antisymmetrize this in mu and nu, which amounts to an antisymmetrization alpha and beta, which will be 1/2 the commutator. Okay, so this is 1/2 the commutator of A mu with A nu dx mu dx nu. Now in an abelian theory, of course, this vanishes, but in the non-abelian theory, this is non-vanishing. And it's exactly what I need to write the field strength. So F then is dA minus I A square, because if I write it out, this is, I get a half d mu A nu minus d nu A mu minus I, the commutator of A mu with A nu, dx mu dx nu. So that's exactly my F mu nu. Okay? So F is a half F nu dx mu dx nu, and you get it in terms of these matrix valued 1 forms as dA minus I A squared. Very convenient, compact notation. Okay? The gauge transformation of A, okay, the gauge transformation of A, delta A, well, it's d epsilon, and then there is the commutator term, right, instead of delta A mu, now we write it for the form, and you just get this expression here. And we can introduce a covariant derivative 1 form as dx mu d mu, which is d minus I A. Okay? Okay, now comes a point in my notes at this point, and it's customary sort of to get rid of all these i's. One does some redefinition by introducing a new A, which is minus I times the old A. But on the blackboard, I will not be able to make a difference between 2 different ways of writing my A. So I will not be, right? So if you do this, then this is just D plus this straight A. But of course, on the blackboard, there's no way to distinguish between this A, and you usually do some redefinition of the generators to absorb i's. So from now on, I equals minus I equals plus minus 1, sort of. No, not really, not really. It's just that I will keep on writing A's, and sometimes if you're on the notes, you know which A I'm talking about. And in the end, I will be precise again, but sort of in the meantime, I have no way of distinguishing the different things, and it will get a little bit disordered. Okay. Okay. So, okay, now we will deal in general with non-trivial spacetimes that may have non-trivial topology, And as I said, you will need to cover our space-time with various coordinate patches. So we call this U1, U2, U3. And there are various overlaps on which we need to know. So on the overlap UI with UJ, we need to know how the things are patched together. Okay? Well, for the p-forms, it was very easy. P-forms are scalars. And now, of course, A is a 1 form, F is a 2 form, and you may well say that, well, they are trivial, they are just equal on the overlap. But now we have a gauge theory, and physically the only thing we want is that if I have an F on coordinate patch 1 and an F on coordinate patch 2, the only thing I want on the overlap is that these two things are gauge equivalent. So I may well allow that F2 on the overlap, where I can compare it with F1, is a gauge transformed of F1. Okay? So on the overlap, Fi should be, which way I want to write it? Fi should be Gij minus 1 Fj Gij, where this is an element of my group, of my gauge group. Okay? So this is on the overlap. I have coordinates x or x prime, doesn't matter. So it's a gauge transform. Okay? Fi is gauge transformed of Fj on the overlap. Okay? Now, Fi is made from some gauge potential Ai and Fj from gauge potential Aj, and then it follows that Ai should also be the gauge transformed of Aj. So this is Gij minus 1 Aj plus d of Jij. Okay? So for A's, which are 1's forms, I get an even more complicated transition rule because gauge transformations for A involve these inhomogeneous terms. Okay? So these relations tell me how I construct my gauge configuration as I go from one coordinate patch to the other. And these transition rules contain important information, and we call this construction the gauge bundle. And we say that these transition functions Gij contain the so-called topological information about this gauge bundle. So let me give you a very simple example. Now we're going to look at a very simple gauge theory, which is U1 gauge theory, which is called electromagnetism. And we forget about time, so we are just looking at static configurations again. So our space in the first place is R3, but not exactly. Okay, and so I take space to be R3, except that I cut out a little ball at the origin. Okay, so M is 3 less a little ball. So something, how can I call it? Less R less or equal R0. Okay, a little ball of radius R0, which I cut out. So then I have some non-trivial space-time, and I will cover it by 2 coordinate patches. One is everything above, and the other is everything below. Okay? So this one I call U plus, and this I call U minus. Okay? Well, you could define U plus U minus in terms of polar angles. So then, you know, one goes a little bit like this, the other like this, doesn't matter. What I need is that there's some overlap here, where U plus and U minus overlaps. So the overlap of U plus and U minus is essentially this plane here, the plane with a little disc cut out. So if I look on the overlap, it looks like the plane with a little hole cut out. Okay, that's view from above. Okay, so now I will define on this space a U1 gauge configuration, a gauge bundle. Okay, so on U plus, I have a gauge connection A plus, which is gamma 1 minus cosine theta d phi. Okay. Now again, d phi is ill-defined for theta equals 0, so on the z-axis. Okay. But on the z-axis, the part of the z-axis that is contained in U plus, so that's this here, that's theta equals 0. At theta equals 0, the cosine is 1 and 1 minus cosine vanishes. So A plus is well defined everywhere on U plus. Okay. Now if I try to extend the definition of A plus to the lower part, I would of course find the negative z-axis with theta equals pi, where the cosine is minus 1 and then 1 minus cosine would be 2, and I would have a problem because d phi is ill-defined at a place where this 1 minus cosine doesn't vanish. But I only define A plus on the upper half, and similarly on the lower half I'm going to define some A minus as gamma minus 1 minus cosine theta d phi. So on the lower half, where the z-axis corresponds to theta equals pi, minus 1 minus cosine theta vanishes, and this is again well defined. Okay. Now from A plus I get an F plus. This is abelian, that's just dA plus. So dA plus is, you get the d of this, so that is gamma sine theta d theta d phi. And from A minus I get an F minus. Well, it's only the one which is flipped, but the one goes away when I take the exterior derivative. So that's also gamma sine theta d theta d phi. Okay? Get the same F. Good. Now, if this is to define a consistent gauge bundle, then A plus should be the gauge transform of A minus on the overlap. Well, they define the same field strength, so it's probably okay, but what I really need is A plus minus A minus. So my gauge group is U1. So this should be I some transition function G plus minus minus 1 G, D of G plus minus, right? That's how things should be related. For an abelian gauge tree, I only have the D because G minus 1 AG just gives me A. Okay, so let's see what is A plus minus A minus. A plus minus A minus is this minus this, so the cosine goes away. It's 2 gamma d phi. That's 2 gamma d phi, which is a, well, 2 gamma d phi is a well-defined one form, except at, well, here it wouldn't be well defined, but my overlap is everything outside this little disk cut out. So that's a well-defined one form on the overlap. Okay, and this should be I G minus 1 dg. So G must be e to the, what is it? Minus 2I gamma phi, right? Minus, yes, minus 2I gamma phi. That's my G plus minus. Okay. So that's my transition function everywhere on this overlap here. So everywhere in here. So as I go once around, phi changes by 2 pi, and this must be single valued. So this is single valued under changing phi into phi plus 2 pi, provided gamma is half an integer. Gamma equals k over 2, so that's in z over 2, okay? Gamma must be half an integer. Okay, so that's a well-defined gauge bundle. Now let's see what's the interpretation of this. Let's compute the magnetic flux through any sphere that surrounds this little ball we have cut out. Okay? So let's compute the integral of this two-form F, the field strength, over any sphere. So I take a sphere here, up, any sphere that surrounds my little ball, and I want to compute this thing. So, well, that's the integral over, I have to use my two coordinate patches, over an upper half sphere, which is S2 intersected with U plus of F plus S2 minus of S minus. But of course, F plus is the same as F minus, and that's just the same as integral of F over the whole sphere. But F is just gamma times the volume form. So we get gamma times 4 pi. And because we know that gamma must be k over 2, we get 2 pi times k. Okay, we get some quantized flux. This thing, of course, F is the magnetic field. We're computing the, so this you would call the flux of the magnetic field through the sphere. So there's some magnetic flux. So there must be some magnetic charge somewhere. Now, we know that if F is dA, as long as F is dA, we cannot have any magnetic charges. So there cannot be any magnetic charge in my manifold. So the magnetic charge must sit here, okay? Which is not part of my manifold. So we have some magnetic monopole. There's a magnetic monopole at the origin, which is not part of my manifold, and this gives me this magnetic flux. Now, the amazing thing is that we find that this magnetic charge is quantized in terms of some integer k, which we just got from these topological considerations of patching together the two, the A plus and the A minus, with a single valued gauge transformation. Okay? So this gauge bundle is called the monopole bundle, and that you get an integer. Let me do the same computation again. Okay, so the integral of F over S2, I write it like this, and then F plus is dA plus, okay, over S plus, and F minus is the dA minus, okay. So now I have two integrals of two exact forms, d something, and I can use Stokes' theorem. So this thing here is the integral of A plus over the boundary of the upper half sphere, okay, and this is the integral of A minus over the boundary of the lower half sphere. So what are these spheres? That's my upper half sphere. That's my lower half sphere. So the boundaries are just these circles in the equator. Except that the orientation of the boundary for the boundary of the upper half sphere and the lower half sphere are opposite. So once I have this boundary, once I have the other boundary. So this equals the integral of A plus over the circle in the equator, and this is also the integral over the equator, except that the orientation is reversed to get a minus. So that's the integral over a circle of A plus minus A minus, okay? So the circle is the overlap of these two spheres, but A plus minus A minus is exactly given in terms of this transformation. Okay. So this thing is given as one of I g plus minus d g plus minus minus 1. So the important thing is that this whole integral of f over the compact sphere is given just in terms of the transition functions between a plus and a minus. And it's because this transition function had to be single valued that it was given by e to the minus ik phi, and we got this integer coming into the game. Okay. Now, why do I insist on this example? Because it's sort of the it's amazing that we compute the integral of some field strength f, and we find that it's given by some integer. Okay. And that's the simplest example of what's called a characteristic class. Okay. So integral of f over some two-dimensional manifold, compact, that's called a characteristic class. And as we've just seen, it only depends on the transition functions of the gauge bundle on the overlaps. Okay? And for this reason, it's related to some integer. Now, not today, but tomorrow, we'll discuss more generally characteristic classes for non-abelian gauge theories. So this will be made from traces f wedge f wedge f p times. So that's some 2p form, which we can integrate over a 2p dimensional manifold. And typically, these things will only depend on the transition, on the transition functions on the overlaps. So there's a certain, in a way, they are robust to deformations of the gauge fields, and they are more or less related to integers. So these things are what we call topological invariants. Okay? So I will have to say more about them tomorrow, but they will be important for our characterization of the anomalies. So let me just give you sort of a preview. So these things are closed forms, but we will be able to, well, locally these things are given by d of something, okay, some 2p minus 1 form, and these, although these things are gauge invariant, these 2p minus 1 forms will not be. So these guys are called the Chern-Simons forms. Okay. So these Chern-Simons forms are not gauge invariant, but if we look at the gauge variations of these Chern-Simons forms, they will be related to some exact forms, which are 2p minus 2 forms. And it's these things that will be related to our anomaly. So we will go through all this characterization and show that in general our anomaly will be given by this thing here. Okay, but it's time to stop.